Yes, yes, very well.
Okay. Let me try to put on my slides. Here. Window. All right. So can you see it? Oh.
Yes, it's yes, yes, we see it very well.
Okay, great. Okay, everybody. Should I say good afternoon? It's early morning here. But anyways, very happy to give this presentation, and thanks for inviting me. So my talk, the title of the talk is a generic Galilean invariant MRT collision model for a Lattice Boltzmann method. This is some work that we did in the past 12 years. So I'll just try to give a update on that. So the background, I'm going to talk about the background, and then I'll go to the detail of this Hermite expansion-based MRT. There are three parts: the general idea, and the central moment version of the MRT, and last I will talk about the symmetry and the maximum number of relaxation time that we can include in the model. So the problem that is very well known, we have this Boltzmann equation, and with a very complicated collision term, which is often modeled by a simple expression. And the second line is probably the most popular phenomenological collision model, the BGK. Very popular, but with some also very well-known problems. I think the number one problem is that with this model, everything relaxes at the same relaxation rate. So you got non-physical artifacts such as the unity Prandtl number, and also your bulk viscosity, if you have one, it's going to be the same, or a fixed ratio with your shear viscosity. The motivation of this work is how to solve this problem, and that we can extend the model to a more flexible applications. So this is actually a kinetic theory problem, and it's a problem with the BGK. So in the past, there are like a few modifications proposed a long time ago. And the most well-known one is perhaps the so-called Shakov model. And also there is this ES model, both of which propose to modify the equilibrium distribution and to introduce some additional parameters into the equilibrium distribution. Actually, in the Shakov model, the Prandtl number is explicitly dialed in, so that at the macroscopic scale, you have that number built in. Also in the Lattice Boltzmann, there is this very well-known MRT model, but in the discrete velocity space. And I think this is started in 1994 by Dumier. And the basic idea is that you decompose your distribution function, the non-equilibrium part of the distribution function, into eigenstates that represent the important movements, and then the collision term become a matrix that you can diagonalize it, and then the diagonal values are the eigenvalues which you can tune, or you can make them to represent different relaxation rates. Although many of those eigenvalues are bound together, they are not free due to symmetry or isotropy requirements. There are a few degree of freedoms, additional degree of freedoms that you can explore to change your relaxation times of, for example, the thermal modes. There are some problem with that. Like this model has like 26 years of history, but I think all the lattice that this kind of MRT model used are the standard D2Q9 or D3Q1527, whatever. None of those models are able to represent higher moments, for example, the third order moments, so that you don't even have a valid thermal equations, let alone a Prandtl number. So it does not serve the purpose of having the variable adjustable Prandtl number. And also the matrix M is lattice dependent. If you have a different lattice, you have more velocities, then you have to redo this eigenvalue decomposition, and it could be quite complicated. And the third problem is that we know the hydrodynamic equations are determined by the moments of your distribution function. And this is in the continuum space, like you carry out the integration, but this integral normally is not necessarily the same as the discrete version of it. Like if you do a summation, the summation is not always the same as your integration. So that to show your macroscopic equation is what you want, you have to carry out a Chapman-Enskog calculation to get the real hydrodynamic equations. And also, actually, this model is popular because it has improved the numerical stabilities. Actually, the same kind of improvement can be achieved with the so-called projection method. You can truncate the higher order components of it, and then get the same kind of effect. And also, a number of years ago, we proposed to do the MRT in the spectrum space. Basically, we expand the non-equilibrium part of the distribution function in terms of the Hermite polynomials. So the BGK model is just the non-equilibrium distribution function multiplied by a factor 1 over tau, and this new model is simply move the factor inside the summation, and then so that it can change. So this way, you are not limited to fixed lattice. This is also lattice independent. If you use a higher order lattice, which allows a higher moment to be included, then you have the freedom to tune your relaxation rate to achieve the thermal independency from the viscosity. So we do achieve the variable Prandtl number, but the one leftover problem was that the thermal diffusion is not Galilean invariant if the Prandtl number is not 1. So it's kind of not perfect. And but in 2014, Hudong published a paper saying this problem can be fixed by adding some additional terms into the third movements. So the paper is at the bottom. So now this, in the past few years, we show this can be done more systematically. So it starts by looking at the procedure that you go from your conservation equation to the so-called Navier-Stokes equation. So we know that the critical part is that you have the second movement, the pressure tensor P, and the part of the third movement, which is the heat flux S. As long as you have those two movements calculated from your non-equilibrium distribution function, then you're fine. You don't care about what exactly the distribution function is. You only care about these two leading movements. If you do that, then we go back to the so-called first order Chapman-Enskog with the BGK model. It boils down to the top of the line expression. Actually, if you look at the statistical mechanics textbook by Huang, for example, the procedure involved in this derivation only requires that the collision term satisfy these two conditions. That is, the second movement of the collision operator is a constant times the F1 second movement and the third movement the same. So you only need these two expressions so that you can recover the Navier-Stokes. Now we can extend this idea, saying if this is what it takes to get the Navier-Stokes, can we extend this two expressions to actually define the entire collision operator. So the condition is this, is the last line. So you say the collision operator must satisfy this condition. So now you have introduced a series of collision times, a spectrum of that, actually. So this is corresponds to the spectrum theory of differential operators. For any linear operator, you can always like decompose it into its eigenstate and assign eigenvalues to different eigenstates, so that you can have the entire operator defined by a series of numbers. So by doing that, you essentially move to the central moment space. You calculate your moment in the relative frame. But we all know a part of this lattice Boltzmann scheme. The advantage is that it's simple, and then there's a simple advection collision procedure, which requires that your discrete velocities be fixed. It's not moving with the fluid, so that when you take the derivative of that, it's zero. It's a big advantage. So if you don't want to abandon that advantage, then you have to go back to the absolute reference frame. So there are many different ways. Like in the literature, some people use the interpolations to go back to the absolute rate, or like to calculate the relative Hermite expansions. But here we use the so-called binomial transform. Actually, there is a relation between the central moment and the raw moment, which is called the binomial transform. But you can do that actually simpler just by expanding these CNs. So these are, C is C minus U, the peculiar velocities. You can expand Cn in terms of Hermite polynomial in the absolute reference frame, C. So if you do that, then you have a series of absolute Hermite expansion coefficients. You can get a expression of that, and what you can see is the last part on the slides. For the second movement, the central moment and the raw moment actually are the same. There's no difference because the first two expansion coefficients are zeros. For the third movement, you got additional term, which is U times A1. Actually, this is exactly the same as what the Houdon proposed. They calculated nonlinear Stokes equation and get this term explicitly. But here from the central movement idea, you got the same result. And also, moreover, you can do this for higher moments. The fourth moment result is like given here, and so this is a numerical verification that shows we have fixed this non-Galilean invariant. So in this test, we measured the sound speed, thermal diffusivity, and viscosity in a shear wave setup. So the whole setup is on top of constant translational velocities. So just to test the Galilean invariance. And we can see that the red part is the previous model, the 1907 model. The blue one is the previous model. Everything stays low. So this shows the error. So except the blue circles, these are the thermal diffusivity in the MRT model. Actually, if you plot this data in linear plot, this is actually a straight line proportional to U0. You see this deviation has been fixed with the central moment models. So the last topic that I'd like to talk about is now you can, a natural question to ask is that why assign one number to the entire Hermite polynomials? What's the reason for the whole polynomials to have a single relaxation time. Actually, the Hermite polynomial has multiple components. Why not assign separate numbers to separate components? Actually, this is due to the constraint of the symmetry. We know the fundamental requirement for a physics law is that it shouldn't be affected by spatial rotation. The question is, can we do this in a finer-grained way without breaking the rotation symmetry? So if we look at the group theory, and we find that there is a mathematical result called the irreducible representation of SO3, the rotation group. And each tensor, like a rank 2 tensor or rank 3 tensor, they all furnish a so-called the irreducible representation of SO3. For the rank 2 tensor, the result is any tensor, second-order tensor, you can decompose it into 3 parts, which are the traceless symmetric tensor, and a anti-symmetric tensor, and a unit tensor multiplied by the trace. So each of those 3 parts are invariant under spatial rotation. That means if you do a rotation of either of the parts, they stay within themselves. The traceless symmetric tensor, if you rotate it, is still a traceless symmetric tensor. Same is true for the anti-symmetric tensors. But in our purpose, the the Hermite polynomial and its coefficients are both symmetric tensors. They're not trace-free, but they are symmetric, so that we don't have the second term. We only have the first and the third term. So in group theory, so this decomposition sometimes is written as the oh, am I passing my time? Sorry. It's a 3 by 3. This is the second order 3-dimensional tensor can be decomposed into 5 plus 3 plus 1. 5 is the traceless symmetric, 3 is anti-symmetric, 1 is the unit tensor. So that the point is the minimum unit that you can separately manipulate or separately relax is this 2 parts, the traceless symmetric and the trace part of the unit tensor. And but for a LPGK model for a monatomic gas, due to the conservation of translational kinetic energy, you don't have a trace. Your pressure tensor is traceless from the beginning, so you don't even have the third rank, the third part. So to show the effectiveness of this decomposition, we have to go to a model with a trace. So we go to the SRT model for a polyatomic gas, and this one was published in 2008. Basically, you represent the dynamics with a pair of distribution functions, 1 and 2. 1 is the normal one, distribution function with the Maxwellian. 2, you multiply the FEQ by theta. Theta is your time. And the theta is related to the total kinetic energy, epsilon. And the total kinetic energy is defined by this last expression. It's 2 parts. One is from F1, the other is from F2. So in this paper, we show that this system gives you the variable ratio of heat capacity. And basically, you have the model for a polyatomic gas. This one, the translational kinetic energy is not conserved, so that your pressure tensor does have a trace. And now we can decompose the collision term into the irreducible components. These are, the final result. So in this model, you have 4 relaxation times from the leading term. Actually, the 2 of them must be equal due to energy conservation requirements. So you end up with 4 relaxation times. So 1 controls the shear viscosity, and 1 controls the bulk viscosity, and the third one and the last one controls the heat flux of translational kinetic energy and the kinetic energy of other degrees of freedom. And so actually, that's the end of my model. Hopefully, I'm not over time too much. Thank you so much.
Sorry, Shawen, I was talking with my microphone silenced. This is the issue with the remote. Thank you very much for your very nice and inspiring talk. Are there any questions from the audience, please? Please, Professor Karlin, yes.
Hi, Simon.
Hi, Ilya, how are you?
I'm doing these days. That's my question. How are you doing?
I'm sorry, I didn't hear that. Can you say it again?
How are you doing these days?
Oh, I'm doing fine. I'm in Seattle.
Okay, I got the answer to my first question. So my second question is, in the plot you were showing, so this measurement of the what you call the Galilean invariants. So what was the number of speeds you're using? Is it
number
90?
The number of velocities. So this one in 3D we used 103.
103. And
yes.
In 2D?
In 2D, I remember it right, the 37.
Okay. Okay. So you really need a lot.
Yeah.
Okay.
Yeah, actually you can trim most of it.
Fair enough.
Right.
Okay.
Thanks. Other questions, please? Okay, so we can thank our speaker one more time. Thanks again, Shawen. Thanks for being with us and for your kind presentation. So now the sessions will split into the two rooms, as I told you before. We will continue with our next speaker here in Sala Leone. Then will be the technical session shared by Professor Bogosian in a virtual room Palma. So if you are going to present or to attend the other speakers, you have to attend the other room. Okay, so now we can go to our next speaker, Dr. Reyhanian. I hope I have spelled it quite good. And please, Shawen, you should stop your presentation, please. Okay, thanks. And I leave the floor to the next speaker, Dr. Reyhanian, from the group of Professor Karlin. Okay. I think that you have your microphone silenced, so please, you should turn it on. Okay.
Hello?
Okay. Yes, we hear you and we see your presentation. That's very good. Thanks very much.
Yeah, sorry, I have to redo this again. Present again, sorry. Okay, now I hope my screen is visible.
Yes, we see it. Please,
okay.
You can start.
Good afternoon, everyone. My name is Reyhanian, and I will be presenting today about our recently developed model to simulate non-ideal fluids. The lattice Boltzmann method have been successfully used to model multi-phase flows. Various models have been proposed to date and validated by different benchmarks. It has been shown that the characteristics of non-ideal fluids, such as phase separation, phase change, or surface tension, can be captured by LBM. More practical applications such as the impact of a droplet on textured surface, which is of engineering importance, have also been studied with LBM. However, due to the inherent restrictions associated with lattice Boltzmann schemes and also the complexity of multiphase flows, many models have remained in the compressible two-phase regime, whereas we know that there are more to non-ideal fluids other than just the subcritical two-phase region. For example, one could talk about the supercritical flows. Therefore, simulation of compressible non-ideal fluids within the kinetic theory framework is still an open subject. This is a very demanding field to study. Since there exist many experimental as well as numerical and theoretical attempts on subjects such as the interaction of a shock wave with bubbles, droplets, or, for example, water columns. Hence, we aim to construct a thermodynamically consistent model in the kinetic theory framework that can handle supersonic non-ideal fluids. Now, LBM is usually recognized with a set of symmetric discrete velocities with corresponding weights for each direction. It is common to use a polynomial equilibrium function up to second or higher orders in velocity. This truncated equilibrium function is the main reason that the conventional lattice Boltzmann schemes are not Galilean invariant. Although many attempts have been made to reduce the errors rising from this issue, no full Galilean invariants have been reached. More importantly, these attempts are usually associated with using high-order lattices, which means more expensive computations. However, in the context of the particles on demand, or what we call POND, we talk about the reference frames. Now, the conventional discrete velocities or the peculiar velocities here are realized as the relative velocities with respect to the imposed reference frames. So what we do here is that first, the conventional velocities are rescaled by the local information from the pressure and density field, and then they are shifted with the local velocity of the flow. So the former here leads to thermodynamical consistency, since now the non-ideal pressure can be inherently included by local operations instead of non-local forcing, for example. And here, shifting the velocity at the and being at the co-moving reference frame will bring us the exact equilibrium, and hence full Galilean invariance. So new set of adaptive velocities which contain information from local thermodynamical field and the local velocity of the flow, of course, will lead to a thermodynamically consistent and Galilean invariant model. Finally, one could observe that the present scheme would reduce to LBM if the pressure is chosen by the ideal gas equation of a state with the lattice temperature, which is what inherently recovered by LBM, and if the velocity reference frame is set to 0 globally. In our simulations that I'm going to show in the next slides, all of our root basic lattices or the peculiar velocities are chosen from the D2Q9 lattice. So only 9 velocities are used. So the streaming step, which is a simple shifting operation in LBM, is differently done here, where a predictor-corrector process is required. Now, for the sake of the presentation, first, I consider the isothermal case where one population is only needed. And given that the new velocities are no longer symmetric and space-filling, a semi-Lagrangian advection scheme is adopted. Here, the information at the monitoring point X is updated by traveling back in time through the characteristics where the departure point is reached. And since the departure point is an off-lattice point, a number of few collocation points around the departure point is needed to interpolate for the desired information, or in this case, the F population. Now, once the semi-Lagrangian advection is completed, the density and velocity field, as well as the pressure field, are computed, and then the same process will repeat with the new imposed reference of frames. And this iteration will continue until the convergence of the reference frame is reached. And after that, finally, the collision step will follow with the exact equilibrium function. Now, any compressible model must take into account the energy conservation properly. Now, as a paradigm for non-ideal fluids, we chose the well-known van der Waals equational state, where the internal energy of such a fluid is not only a function of temperature, but also a function of density. This calls for using a second population to conserve the total energy of a non-ideal fluid. Now, the algorithm is the same for as the isothermal case, only that the pressure now is a function of both density and temperature, where the temperature is computed from the total energy conserved by the second population. And finally, I should mention here that the Fourier heat flux recovered from the Chapman-Enskog expansion applied to this method recovers the gradient of enthalpy instead of the temperature. So although this is justified as the limit of an ideal gas where the enthalpy is only a function of temperature, this must be corrected for a non-ideal fluid where enthalpy is also a function of pressure as well. Now, I move to the test cases. As I said, our lattice is a 9-velocity lattice. And here I present the simulation of the speed of sound at two different setups. The first case considers as an isothermal simulation, while in the second case, the energy conservation is also taken into account. And here the simulations can be addressed as isentropic. Now, for the two cases, we find a great agreement with theory for both the liquid and vapor phases at different reduced temperatures. However, it is clear that the speed of sound in an isentropic setup is significantly larger than the isothermal setup, as expected. Now, what distinguishes our model from conventional lattice Boltzmann schemes is that the isentropic speed of sound for a non-ideal fluid can be correctly captured even at the critical point. And thanks to the exact equilibrium, we are able to handle large values of velocities, particularly in the liquid phase, which we can see here in the vertical domain, vertical axis. Now, for my second case, and as one of the most fundamental concepts in thermodynamics, I would like to present the simulation of the inversion line. The inversion line is defined as the locus of states with 0 Joule-Thomson coefficient. This is specifically important in a throttling process, where the enthalpy remains constant while the pressure drops. The subject of the inversion line is only meaningful in the context of a non-ideal fluid, since the Joule-Thomson coefficient is 0 by definition for an ideal gas. Now, in this simulation, we aim at measuring the value of this parameter at different supercritical states and construct the isentropic lines in a PT diagram. In order to do that, we measure two quantities that appear at the definition of the Joule-Thomson coefficient. First, it is the isothermal speed of sound, which we have already covered, and the other one is the variation of pressure to temperature at fixed density. Now, to measure this quantity, we consider a domain with an initial pressure and temperature, where the flow inside the domain is subject to constant acceleration. During the acceleration, the pressure drops. And consequently, the temperature also drops linearly with pressure, where the density is remained fixed. Now here, the slope of the PT curve can be measured readily and plugged into this equation. Simulations have been conducted along 3 different isentropic lines at different states, where the reduced pressure ranges from 3 to 15, which is far into supercritical flows. Finally, we see a very good agreement with theory and the simulation, and we can see visibly clearly here the effect of the inversion line, which is the locus of the 0 0 points of the Joule-Thomson coefficient. Now, for the next test case, I would like to talk about the shock stabilities in a non-ideal fluid. In the study of shock wave stabilities, exotic behaviors can happen. For example, if the Dyakoff parameter, which is directly related to the slope of the Hugonnet curve at the post-shock state, would violate the range of stability, a shock could split into two shocks traveling with different speeds. As an other example, if this parameter is larger than a critical value, any initial perturbation on the shock front can remain stationary, and the shock would radiate acoustic waves as it propagates in the fluid. This is also known as the Dyakoff Kontrovich instability. And once again, I have to mention that these are only the characteristics of non-ideal fluids, since a shock is always stable when propagating in an ideal gas. Here, we have chosen a case that could demonstrate these behaviors. A shock wave with Mach number 1.11 is seen to split into two waves traveling with different speeds. Now, by applying initial perturbation on the shock front, we can observe a very interesting phenomena. First, the shock is split into two other shocks. The first shock starts to emit sound waves as it propagates, and the second shock, that moves slower, undergoes a Richtmeier-Meshkov type instability. Now, this is very important here to notice that by using only 9 velocities, we have captured 3 instabilities, where we have interaction of shock waves, acoustic waves, and deformed interfaces. Finally, in order for the model to perform in the two-phase region properly, the excess energy of the interface must be taken into account. To that end, the post-collision populations are augmented with proper source terms, and where the effect of the Korteweg stress is introduced by the population SI, and the effect of the work of that force is introduced by the population GI in the energy equation. Now, we recover the full Navier-Stokes equation by conducting the Chapman-Enskog analysis, and we can get full NS Navier-Stokes equations for a two-phase system with the Chapman expansion. Now, as for the final test case, I present the shock droplet interaction. The setup consists of a planar shock wave with the Mach number of 1.47 propagating into a saturated vapor, where there is a two-dimensional droplet. Now, a two-dimensional droplet can be realized as water column in practice. Once the shock reaches the surface of the droplet, a transmitted wave appears inside the droplet, which moves faster than the initial shock, since the speed of sound is higher in the liquid phase. Also, a reflected shock wave is visible traveling backwards. Now, consequently, the droplet starts to shrink in the flow stream direction and grow in radial direction as it moves further. And for quantitative comparison, the widths of the droplet were measured in non-dimensional time and compared to experimental results, where we see a very good match at 3 different Mach numbers, namely the Mach 1.18, 1.3, and 1.47. And also here we can see the deformation of the interface upon the impingement of the shock wave onto the surface of the droplet. Now, to summarize, our proposed model employs a set of adaptive discrete velocities where the non-ideal pressure can be locally included. The Galilean invariant feature of the model, together with the full energy conservation, enable us to model compressible non-ideal flows. Also, simulation of flows with phase change is feasible with the current method. In particular, the model is able to handle phase change with fast dynamics, which can happen, for example, at large Stephan numbers. Finally, we look forward to extend the current method to a multi-phase, multi-component model with 3D applications. Thank you very much for your attention.
Thank you very much, Dr. Reyhanian. Are there any questions from the audience? Actually, I would have two curiosities more than questions, if possible. First of all, what are the density ratios that are achievable with your scheme? Is there an upper boundary, for instance, 1 to 1,000, 1 to 100, 1 to 50, something like this, which is a major issue in the multi-phase approaches with Lattice Boltzmann? And then, but this is more a curiosity, question number 2, is if you have some issues related to the spurious currents that usually arise, but I have seen the very remarkable results, so I guess that this is not an issue at all with your scheme. Please.
So usually the density ratio can be improved. The range of the density ratio can be improved by, for example, using models such as Cahn-Hilliard or phase field models. But here, thermodynamics is actually more important to us, and for that reason, we have chosen the van der Waals equation of state, which actually is not very wide in the range of density ratios, especially also in the lower temperatures. But it depends on the equation of state that you use. For example, you can use the Penn-Robinson equation of state and go to high density ratios. But I haven't done the simulation, for example, with density range of 1,000, as it is common, for example, in these phase field models. But the common density ratio has been captured by the model, but it also can be improved by having this phase field models maybe in the future. And also for the spurious currents. So spurious currents are usually a result of the imbalance between the gradient of the pressure, which we include as a forcing term, and also the Korteweg stress, the force due to Korteweg stress. And now, since here we do not have that forcing term for the pressure, because now the pressure is locally included, not locally. So these spurious currents are much, much smaller than, I haven't shown here, but I should tell that now that is much smaller than a simple, for example, multi-phase LBM scheme where there is no additional techniques to reduce the spurious currents.
Okay, thanks very much. Are there any questions? Any other questions, please?
Can I have a question?
Of course, please, Shawen.
So yeah, you mentioned there's some interest in modeling the behavior at the critical points. At that point, the speed of sound is very low, and it'll be a very interesting spot to look at. So I'm wondering, can you say anything about what did you observe near critical point for a shock bubble interaction?
For the shock droplet interaction?
Yeah. You see anything interesting there, or I'm just curious, like what's going to happen at the critical point?
Yeah, I don't quite understand the question, because now at the critical point there is no liquid and vapor phases, right? So
close to, very close to critical point.
Yeah, very close to. Well, usually because the speed of sound is decreases as we approach the critical point, actually it makes it easier for the simulations, because now the values of the speed are smaller. But physically, no, I did not see anything specific in that simulation, because, for example, that simulation also is the reduced temperature of 0.9, right? And by having a good scaling that would consider the ratio of the speed of sound at both liquid and the vapor phases, we can have an agreement with experiments which have very larger density ratios and with different temperatures. So no, nothing in specific to say.
All right, thank you so much. Very nice work.
May I add just one comment, if I may, to that?
Yes, please.
And to that way. So just to be a little bit clear on that new model. So the Jackman's question, first question, how big the density ratio can be achieved? So we are somehow used to talk about multi-phase models in the lattice Boltzmann, myself included, thinking that there is just this droplet, vapor, things like that. So we somehow forgot, well, not forgot, but we somehow tend to forget that there are other regions in the PT diagram, so which are supercritical and which go into very high or very much above the critical pressure and temperature. So and so this model tries to explore the field out of the coexistence, more or less, dome towards other. That's one thing. So of course we since we use just van der Waals, we are in the usual range of densities, not super dense like that, but good enough to have also conventional, more or less, scenarios as well. So, and to the experiment, actually, I would like to say that actually we do see very interesting effects near the critical point, not in this particular simulation, but also what we don't show today at the thing like the collapse of the bubble, single bubble, luminescence scenario kind of. So there are effects. So like, for example, the bubble, the vapor, the pressure can suddenly jump too much and the fluid becomes supercritical inside, so loses the interface and then gets it back. So we see these effects, which are also seen in other experiments and so on. So it's, I would say, quite interesting. So I want
yes, also from an industrial point of view for the application
of a Shan that we do not see anything. No, we do see. So
great. Looking forward.
You will see that, and for sure.
Okay, thank you very much.
I'm sorry for this comment, but I wanted to be a little bit.
It was precious. Thanks, thanks very much. Since it is interesting also for the industrial outlook for applications.
Yeah. So we are specifically,
supercritical behavior is very important. Okay, thanks truly much. Thanks. So let's thank our speaker one more time.
Thank you.
Thanks, Dr. Reyhanian. Now we move to the following talk by Professor Wagner, Alexander Wagner, from the North Dakota State University. He needs no presentation, and he has been always very active in the field of non-ideal fluids in the lattice Boltzmann mixtures, and recently also with the large fluctuations in non-ideal fluids. So please, Alexander, I leave you the floor, and thanks for being here with us.
Thank you, Giacomo, and thank you for organizing this conference. I have a small technical problem here, which tells me that I can't share my screen, but I'm just using a different device. See if I can't get it from a different computer here. While I'm setting that up, I'm just make sure I get to the conference here. Okay. I think I have a question. Sorry about that. Okay, so I'll need to restart the browser as well, because it won't allow me to do that otherwise. Okay, let's go to this meet now. I was trying to do it on my iPad, but apparently there's some
issues.
permission
Maybe you could try to log out and log in again. Okay, now we see you two in two frames.
Okay. Sure. I'll turn this one off.
Yes.
Okay, hopefully the echo will go away now. Okay, so you can see my screen?
Yes, we see the screen. Okay, now we see the presentation. Please.
Maybe shut this one up. Okay. That's the echo is gone.
No problem. Yes, we see it very well. Yes, but you have your microphone silenced. You should turn up your microphone, please. You can hide this bar and then you can. Okay.
So now we can hear me?
Now we hear you. Okay, that's fine. Thanks.
Now I got to do the present now again.
Yeah.
Entire screen. Share. Okay. Can you see my screen now?
Yes, we are seeing it. Yes.
And now it's optimizing something. Okay. Okay.
We see the black screen. Actually. Okay.
Yeah, that's the same for
now
me.
We see conclusions.
It'll probably just take a second. It took a second a moment ago,
Okay.
so hopefully that will.
Okay, now it's fine. Thanks.
Perfect. Okay. So I want to talk. So this goes back to probably to what Sauro talked about, the very beginnings of Lattice Boltzmann, so we start off with these lattice gases, and these lattice gases come out of this idea that you can have this very simple statistical mechanical model where you conserve mass and momentum locally, and then you get something that gives you macroscopic mass and momentum conservation equations, which then become the continuity in the Navier-Stokes equation. And that, of course, has noise. And then people went on to Lattice Boltzmann. Now, here we're trying to go the other way around. So if you have a lattice gas, the question is, can you have a lattice gas that's actually just a coarse graining of an MD simulation? So why would you want to do this? So we came to this particular question from the question of fluctuations, and in particular, the problem of what are fluctuations supposed to look like in Lattice Boltzmann for non-ideal systems. And we really just didn't know. And so this was our attempt to get to the answer of what do these fluctuations actually look like for non-ideal systems. And that gives some very interesting answers that I'll get to a little bit later in the talk. But first, I'll just kind of introduce that as MD. Everybody knows MD, so it's basically just solving Newton's equations for a large system of particles. And of course, in principle, that allows you to simulate any of the problems that we talked about, except that it's not very practical because it's just expensive to have that many particles, right? But on the other hand, it's highly accurate and it can inform what your model really ought to do. Now, the lattice gases that we heard about. So Sauer introduced the lattice gases that are these original Boolean lattice gases, and a lot of the things that were difficult with them, turns out, actually had to do with the fact that these lattice gases have this Boolean property, because then the equilibrium distribution becomes a Fermi-Dirac distribution, and it doesn't really become a Boltzmann distribution. Now, you can actually make this an integer value rather than a Boolean value, and that removes a lot of these Galilean invariance problems that people had, and you can recover an integer lattice gas, which is just a lattice gas version of a lattice Boltzmann method. And that is something that I talked about at DSFD before. That's very interesting. It actually recovers an equilibrium distribution which corresponds to the one that Ilya and Santosh and Somali recovered for entropic lattice Boltzmann. So there's some interesting connections here. But so generically, the lattice gas looks like you have here these occupation numbers Ni, which now are integers. They have this advection, just like you have in the lattice Boltzmann, and you have a redistribution of particles, which is this Xi collision operator. And this Xi is typically probabilistic, and it obeys the conservation of mass and momentum that we have here. Okay, now you can think of lattice Boltzmann as nothing but the statistical, non-equilibrium statistical average of a lattice gas. And Sauer gave a nice introduction to that earlier in his talk. And if you do this now, suddenly the Ni's were integers in this case, the Fi's become real numbers, and the collision operator, which was derived from this probabilistic operator Xi, now becomes a deterministic operator. And this, despite the fact that it looks, this equation 7 looks exactly the same as the equation for the integer lattice gases, of course, it means something very different, because these n's were integers and the Xi was a probabilistic collision operator. Here now we have real numbers and the deterministic collision operator. And of course, what it achieves is that you get rid of the noise that was there, and you can also derive, as we heard about earlier, the continuity Navier-Stokes equations out of this. And it's a much cheaper way of simulating a macroscopic system if you compare it to MD. Now, what exactly this collision operator ought to be, that is a very good question. And we heard earlier the contribution of Demir and Kian of introducing the single relaxation time, basically the BGK approximation, which is a very typical one. And you get the viscosity given by tau minus a half in here. And theta is chosen to be 1/3, and this gives this BGK approximation. There's one other interesting aspect here, which was also referred to earlier in the talks, which is that if you have a lattice gas, all it can do, it can maximally do, if you have these collisions, can bring it to equilibrium. But all the beautiful simulations that we saw just in the talk before have to do in the regime where your viscosity is, where you have your tau close to a half, or where your viscosity is very low, and then you get these nice turbulent behaviors, which normally you can only achieve in a lattice gas if you have a large enough system for this. And this is something that I'll allude to towards the end of the talk again. And there is a small industry to develop better lattice Boltzmann collision operators, as in MRT, entropic, cascaded, cumulant collision operators, which have nicer properties, and then of course extensions to fluctuating systems and multi-phase and multi-component systems. And how you do this is always derived by what you can simulate in terms of macroscopic equations, but it's not really as much motivated from the microscopic underlying physics. Now, here comes the idea. What we can do instead is we can map a molecular dynamics simulation onto a lattice gas. And this may sound like a crazy idea, but think of this as a way of obtaining the ground truth for what a lattice gas ought to look like, or if you then take your averaging of this, what a lattice Boltzmann simulation ought to look like to actually recover the same physics as that was given by your MD simulation. So the MD simulation gives you like ground truths of how your system ought to behave microscopically. And you can't get that information from these Chapman-Anscombe expansions because those are all long wavelength simulations. So anything that is inherently small scale, you can't really derive from this high dynamic limit. And if you can get some information about how this microscopic behavior ought to be, that is an enormously powerful tool, certainly to understand fluctuations, which is how we got to this, but also in terms of understanding what collision operators ought to look like, what equilibrium distributions ought to look like, and a whole host of similar problems. So how do we do this? So you can see here this, I can't see my mouse, so I'm sure you can't see anything either, but you see this, these green little dots, which are the atoms. They, if you let them run for a certain amount of time, this is just some set of tracer particles, they'll end up in a new position. And overlaid on this, you then have this red lattice, which gives you lattice boxes. Particles are in some of these red boxes. And these boxes are then associated with this lattice gas, lattice points, which are given by the crosses in the blue lattice. And this blue lattice now has these black lattice vectors that go from the center of the blue lattice to the neighboring points. So this would be just in the last talk, this D2Q9 model. And you can just measure, given a certain amount of delta t, where do these particles move to? And so that tells you then what are these occupation numbers Ni, right? You just look which particle moved from this cell to that cell. That is your Ni for that time step. And that's really all there is to this. It's a very easy thing to measure. And then you can define your, since you know all the ends at all times, you can then define what your collision term has to look like. If you define this collision term as the difference of the Ni's, then you get this equation 12 here, which looks exactly like a lattice gas evolution equation, right? So this now gives you a lattice gas that behaves exactly as the underlying MD simulation, the coarse-grained version of that underlying MD simulation. And the benefit of this is now you have a lattice gas that does exactly the right thing. And all you have to do now is to examine how this lattice gas behaves, and then you can see if you can find some simple rules for how psi has to look like. So that's similar to what Stefano talked about. So now you're trying to find a pattern for what does this collision operator look like given the data that you have. And you can run the simulation to obtain lots and lots of truth data. And so what we are doing here now is mostly analytical predictions for what it looks like, but this is also, I think, a very interesting starting point for machine learning of a better lattice Boltzmann, which is what Saru alluded to at the very end of his presentation earlier today. So what does this look like? So you all know what an MD simulation does, but I'm just kind of showing here. So we've painted all the particles that start up at the early time in the center box with red particles, and the others are painted blue, and then you can just evolve it as a function of time. And then as time goes on, these particles will move on to the next lattice points. And so for a certain amount of delta t, this gives you certain Ni's. We're just seeing where these particles happen to move to, right? Now, if you want to analyze it, the first question that comes up is, of course, always, what is the equilibrium distribution? And you calculate this by looking at the expectation values of the Ni's. We're looking at a system in equilibrium. So in principle, that contains the n particle function for the displacements of my particles. With these delta functions basically tell you whether this is in the box 0 and then whether it's going to be the next time step in the box vi. And you can integrate everything out, and you just get the one particle distribution function. And you can find an analytical solution for this if you make the assumption that this equation 13, that these displacements are Gaussian. Now, that is another very interesting question, and we just recently found that that is not the case, that they're not always Gaussian. There's a ballistic regime and a diffusive regime where it's true, but in between it's not quite true. There's this archive reference down there, but if you make the assumption that they're Gaussian, which is approximately true at the very least, then you can analytically calculate what this equilibrium distribution looks like. And here you see as a function of basically delta t, this a squared tells you the mean square displacement over the lattice spacing. So at very early times, for very short times, you have very small a, and for larger times, you have larger a. And so, of course, if you only look for a very short time, everything remains in the central box and hardly anything happens. And the longer you wait, the more they will move into neighboring cells. And there's one curious point here, which is that a squared equals 1/6, where the occupation numbers are, to very good approximation, exactly those of the Wi that you get for D2Q9. And so we have the Lattice-Boltzmann equilibrium equation here in 14, which is this polynomial expansion. And then we have this equilibrium distribution of 15, which is also known analytically. It is not truly D2Q9 because there's no cutoff, but if you look at the order of magnitude, you can see that this black, red, and blue at that point are the only ones that contribute significantly, and there are other ones, but they're very small, so they're negligible, essentially. And only for larger times do those also become important. Okay, so this is very nice because it tells us that we can make a direct connection to the typical equilibrium distribution that Lattice-Boltzmann uses, and this coarse graining of molecular dynamic simulation. Now, this, of course, is only at u equals 0. Now let's look, how does this behave for different u's at this particular value? And here you can see the different occupation numbers for different velocities. And you see that for small enough u, so u up to, say, 0.1, they agree well. And now, of course, these systems, they're not D2Q9. So if you have velocity of 1, it does something similar to what Ilya was describing earlier when they do this Galilean shift of their own lattices for these high shock numbers. So if they have large velocities, they impose some additional velocity to their velocity set. Something similar happens here, of course, where you would then get occupation numbers for these larger velocities. But it's very encouraging that they look basically the same as the Lattice-Boltzmann equilibrium distribution. Now, let's look at the original motivation of why we looked at this in the first place. So this was the fluctuations. And we wanted to understand what the fluctuation should look like, particularly for non-ideal gases. Now, for ideal gases, we know that these ends should be, well, we know that the density should be Poisson distributed, and you can make the argument that the ends should also be Poisson distributed, right? And this is something that you can impose and vigorously get for ideal integer lattice gases, and you can get it reasonably well for ideal gas fluctuating Lattice-Boltzmann. Of course, for Lattice-Boltzmann, it can't be exactly a Poisson distribution because it's a continuous distribution, and so there's some subtleties there, but you can certainly get something where the moments agree fairly well with that. Now, you can go and you can look at how this thing scales. So the Ni, going with the Fi equilibrium, the second moment has this quadratic term plus the Fi equilibrium delta Ij. And that means that the width of the distribution compared to its mean decreases as the mean increases. So you know, if you now look at larger numbers of particles per cell box, so if you make your delta X bigger, you have more particles in there, the relative fluctuations will decrease and it will eventually become a deterministic simulation. And the way they go away is with 1 over the square root of the number of particles in there. Okay. And that predicts how the importance of fluctuation declines as we increase the lattice size, thereby increasing the average number of particles per lattice site. And now we can measure what these distributions look like, and this looks very encouraging. So we predicted they would have to be Poisson for, so what we now do is we take a dilute gas in an MD simulation, and we can look at now different coarse graining. So if we have lattice boxes that contain about 160 particles per lattice site on average, we find that the total density is indeed Poisson distributed, as are all the so the F0s, the nearest neighbors and the next nearest neighbors in the DGQ9 are all equally about Poisson distributed. And if you now make your box much bigger, you see that certainly for the total density it works well. For the green ones, which is the N0, the rest particles, that works well. See, there's a small deviation for the smaller distributions, but of course it's not entirely an ideal gas, but that works reasonably well. Now the question, of course, is what happens if you do this for non-ideal systems? Well, first
sorry,
of all,
Alex, you have 5 minutes from now. Sorry to interrupt you. Okay,
yeah.
Please, thanks.
Yeah. So what do you do if you have a moderate density? Then you will have to take into account that there will be excluded volume, but the scaling should still be the same. So if you coarse grain your system, the fluctuations will go away, right? So what should you expect for the scaling of the Ni? Now, this is a very curious result that I'm showing you here. First, you see here that the total density, these black bits, are indeed much narrower than the Poisson distribution would be. And these black parts, they also scale, which is the total density that decreases its width in exactly the way as one would expect. But the rest particles don't do that. So they start off at about the same width as you would expect, but then as you coarse grain it and take bigger bits, they fail to kind of narrow down at the same rate. And that's really odd, because you'd expect from statistical mechanics, if you coarse grain your system, so will your fluctuations go away, but the fluctuations of these Ni's in the non-ideal system don't go away. And you can look at this, and you have these black dots here in this graph. They correspond to what you would expect for an ideal system, and these shaded symbols correspond to what our dilute system does, and that works reasonably well. But the non-dilute system, it certainly behaves very differently, and the decay is much less than you would have thought. Now, the question is, can you understand why that is the case? And there's an interesting story, because you can write this down now explicitly, just like we did before. You don't need to understand everything, but what's important is that what enters into here is the n particle probability of these displacements. And that it turns out you need the two particle displacement probability, and it looks very familiar from statistical mechanics, but it's not, because there's very little work on displacements. That is the stuff that enters into here. And one thing that I want to point out is velocities are uncorrelated in equilibrium. So if you know the velocity of one particle and the velocity of a particle nearby, they have completely uncorrelated velocities. You can measure that, and there's nothing there. But it's not true for the displacements. And that's basically because during a finite period of time, these particles will collide and exchange information. And so therefore, they actually become correlated. And this is something that's actually important, and you can measure what these things look like. And we have here an approximation that they decay exponentially, but not that fast exponentially. And you can see here the data is the stuff that you can measure from the molecular dynamics simulation at different densities. And you find certainly this exponential behavior. The lines there are the theory that we show up there, and then the symbols are the measured data. And they agree reasonably well with this theoretical prediction. You can put that into the model, and from that you can get a two-particle distribution function, or the simplest one you can up with that gives you that correlation is one that actually puts in the two-particle correlations in this way. And with that you can get a prediction that certainly recovers the behavior that we've seen. And so the message from this is that if you do look at these lattice gases as a coarse-grained MD, it's coarse-grained not only in space, but also in time, which means the time correlations suddenly enter into these NIs and into the collision rules, which is something that certainly didn't occur to us before we started looking at this. And this is just an outlook that you can now also use the same method to look at the collision operator. And there will be a talk on Thursday at 4:40 to 5 in the virtual Palmer room by Alexander Pachalieva. And the key result is that you can actually recover over-relaxation in the MDLG. So this is a lattice gas that naturally over-relaxes. So that this is not an unphysical trick, but it actually comes out of the coarse graining procedure. But that is something that Alexander will talk about. So that brings me now to my conclusions here. So you can use this MDLB method to extract an exact version of the lattice gas, or therefore then lattice Boltzmann. You can look at the equilibrium distribution. You can measure what the equilibrium distribution should look like, and it agrees with LBM for small mean velocities. But of course, for larger velocities, it shows how it really should be defined. It allows us to predict fluctuating properties of lattice gases for these non-ideal systems, which are quite different from what has been previously expected. And it also provides the first principles derivation of the lattice Boltzmann collision operator. And this collision operator does show over-relaxation, but that is something Alexander will talk about on Thursday. And so now all the properties of lattice Boltzmann have been reduced to finding, in the most general case, the n particle, or often just the 1 or 2 particle displacement distribution functions, which become the fundamental sort of theoretical underpinning of what you need to predict exactly what lattice Boltzmann has to look like. And of course, there's more potential for looking at boundary conditions and a whole host of other possible applications of this. And with that, I'd like to thank you for your attention, and I hope I stayed roughly within the time.
Thank you very much, Alex, for this very nice and impressive talk. Thanks for your kind presentation. We have time for just one quick question because we are a little bit over the schedule. Is there a very quick question from the audience? This presentation was very, very inspiring, but unfortunately we are a little bit tight on time. Maybe we can leave the discussion after the presentation by Alexandra, the next presentation. Okay, so let's thank Alexander another time, please. Thank you very much, Alexander, for your very, very nice presentation. And then we go to our last speaker of today, Professor Paul Dellar. Paul, it's a pleasure to have you here. And Paul is a faculty at Oxford University. He belongs to the Oxford Centre for Industrial and Applied Mathematics. He has delivered very, very interesting papers on the phase mixing with the lattice Boltzmann, and in the recent achievements deal with the relativistic flows. So please, Paul, thank you very much for being here, and I leave you the floor. Sorry, Paul, we actually do not hear you. I think that you have silenced your microphone. Maybe just on the bar below, you could check if your microphone is on or off. If you go with the pointer towards the bottom of your screen, you should see in fact, you see your microphone is silenced.
Okay, how's that?
Okay, now we hear you, but we do not see you anymore.
Okay, that's working on that.
Yeah. Okay, it is going to...
How's that?
What? Yes.
Good.
We see
Great.
that
Thank you very much.
Okay. This is perfect. We have the complete stuff. Thank you very much, please, Paul.
Because I just been panicking that this is also from an iPad. So, okay, so this is very much in the what Saro talked about at the beginning. Is there life for lattice Boltzmann outside Navier-Stokes. In particular, this is going to meet some old lattice-Boltzmann related friends from a rather different beginning. So I'm going to talk about a numerical scheme for the one-dimensional Schrödinger equations. This is non-relativistic quantum mechanics, and then look at it, and looking at its properties suggests that although this was set out only to be non-relativistic, by accident as it were, this scheme has some relativistic properties that are worth investigating. In particular, it relates to how one can take a relativistic picture of quantum mechanics, then transform it back to something that's non-relativistic, and that's going to inspire some discrete transformations which turn this inoffensive scheme for the Schrödinger equation into some familiar lattice kinds of schemes for relativistic quantum mechanics. I'll talk about its convergence properties and some invariants. So the overall message is this scheme can be understood by thinking about it as being a lattice style scheme for relativistic quantum mechanics. So start off with some sort of quantum background to set the scene. Here's the Schrödinger equation at the top. So I've got some wave function psi. I'm evolving. I'm just going to do a free particle in one dimension. And then this Hamiltonian H generates a unitary evolution. I don't know if I can point. That's this thing. So that if H is self-adjoint, this exponential is unitary. So that generates properties like time reversibility, conservation of probability. And we want a numerical algorithm which has these good properties too. So one thing we might do is say, okay, let's discretize regular lattice in space, finite steps in time. First thing we might come up with then is this leapfrog. So we've done a centered difference on the left-hand side, time level n+1, time level n-1, and we evaluate the Hamiltonian on the wave function at the middle time n, and we get this stuff on the right-hand side. But then that scheme turns out to be not so good, which I'll say in a couple of minutes. So instead, we could do this Fort-Frankel version by Wu 1996. So we take the center point, the psi nj, and we replace it with the average one time level forwards and back. So let's see if I can now do, yeah. So that gives us this stencil here on the right, where we've got 3 time levels, n+1, n-1, 4 points, and we miss out what seems like the obvious point in the middle. By contrast, if you do something more conventional like Crank-Nicholson, that you use so-called KD transform, that's this thing, to build a unitary evolution across 2 time levels. So we go from 3 points time level n to 3 points at time level n+1, but the price we have to pay is there's all this nasty implicitness over here. We've got all this stuff with the wave function at the new time in 3 different places, whereas the leapfrog and the Fort-Frankel, that gives us an explicit formula to evolve forwards in time. But then what does it mean to be unitary when we're moving between 3 different time levels instead of just from one time level to the next? So let's look at, first thing to do with a new unfamiliar numerical scheme. Let's look at its dispersion relation. I've tidied it up a bit, made it dimensionless, but it's the same scheme, and I've solved for that psi at the new time step. And then there are plane wave solutions given by this dispersion relation. And for each k wave number you choose, for each alpha, which is the dimensionless scaled mass, there are 2 real roots, so it's unconditionally stable. And here's a plot, Fort-Frankel scheme dispersion relation shown by the green lines. And the Schrödinger equation, the thing we thought we were trying to solve, is this dashed purple thing here. And that's going up like a parabola, whereas the Fort-Frankel, it's a bit too straight and it's going to bend over, so it's got no gradient at the ends. And the other really striking thing is that there's this second branch of solutions down here in green, omega below 0. And that looks an awful lot like something that, if I talk about in a moment, from the Klein-Gordon equation, these dotted lines, if you shift things right. And the leapfrog is shown in the blue. So again, this has got 2 branches. One of them now always goes through minus pi. So this is saying that we reverse the solution every time step. And also it dies at some finite wave number where it becomes unstable. The Fort-Frankel, by contrast, stays stable all the way out to the edge of the, what do they call them? Forget what I call the cell where if we go any further, we just alias back onto other Weyhinners. So this looks very quantum mechanical. We set out to do something non-relativistic, but by accident, we seem to be solving a relativistic equation, the Klein-Gordon equation, rather better than we're solving the Schrödinger equation that we thought we were trying to solve. So in order to talk about this, I need to say a bit about how relativistic quantum mechanics works and how we map back from relativistic to non-relativistic. So here we are. Here's an equation for a one-dimensional relativistic parser. That's the Dirac equation. So now we've got first derivatives in time, first derivatives in space. A speed of light c has appeared. And instead of having one wave function psi, we've got two wave functions that I'm calling u and d. But if we eliminated d by applying the ddt minus c ddz operator to the first equation, we get the Klein-Gordon equation. So we can either have a first order system, that's the Dirac equation, or we can have a single scalar equation, that's the Klein-Gordon equation. So that for these purposes, the two are equivalent. The interpretation, things like what do you mean by probability density are a bit different. But for PDEs, you can transform one to the other. And now I want to do more and take my Dirac equation, do this unitary change of variables here. This is like a Hadamard gate with an extra I in it. And then I can write my Dirac equation as this thing that looks like an abstract Schrödinger equation with an H over here. And then this H has got some mass terms, relativistic mass mc squared on the diagonal, and some space derivatives off the diagonal. So I put the relativistic rest energy, this being a relativistic thing, on the diagonal. So there's a piece of machinery called the interaction picture in quantum mechanics. So it interpolates between the Schrödinger equation I've shown you before, where the wave function evolves, any kind of operators we might want to apply stay constant, and the Heisenberg picture where we make the operators change, the wave function just sits at the initial condition. This picture says, well, let's split the Hamiltonian into a sort of a base bit and a interaction bit, and we'll put in the exact solution with the base bit. So then we get this new thing where we've only got the interaction H doing evolution, and this phi we started with has been replaced by a psi defined like this. Now, if I made the whole Hamiltonian H0, I would transform from the Schrödinger to the Heisenberg picture. If I apply this to my previous system, I can pull out relativistic rest energy to give myself a diagonal Hamiltonian, so that commutes with everything, which is nice, and I get a bit left over, which has got a 0 in the top left entry. It's got the spatial derivatives, and it's got this nasty looking big term down here. But more about that in a moment. And this motivates, in the interaction formalism, doing this change of variables from phi to psi, where I take out this oscillation with the relativistic rest energy. And this was introduced by Pauli as a way of trying to go from relativistic to non-relativistic quantum mechanics. So I turn the handle, I get two equations now for my size, where the plus equation, that's this one, has no algebraic term. All the algebraic term is on the psi minus equation. And now, thinking about my Lattice Boltzmann Chapman-Enskog toolbox, I want to look for slowly varying solutions. So I'm going to balance this. It's a wiggly I term, not a relaxation term, but I'm still going to balance it with the space derivative and say things evolve slowly, so I'm going to get rid of this time derivative. So then, if that's a good approximation, I can solve for phi minus in terms of the spatial derivatives of phi plus, pop it back in this equation, and I get the Schrödinger equation. So it's like solving for the viscous stress through Chapman-Enskog, popping it back in a momentum equation, and then you get the Navier-Stokes equations. And then I can estimate that my psi minus is really small compared to psi plus when my momentum is really small to mc, so that's how it knows it's non-relativistic. And then if I pop it back in my Hamiltonian, the interaction Hamiltonian is small when applied to this kind of wave function compared to the H0 I took out, even though the H isn't small, the particular structure of the wave function makes H on the wave function small. And then there's a little bit of stuff I have to talk about. that a natural thing to ask is that a quantum mechanical system is supposed to preserve an energy, so that's the expectation of a Hamiltonian. I can work out what's called the matrix element, so I put that Hamiltonian between two wave functions and integrate, and I get this horrible long integral. But if I make my slowly varying approximation, I can write it either as mc squared times the phi minus squared, or the spatial derivative of the phi plus squared, which is then exactly the matrix element of the Schrödinger Hamiltonian that I started with. However, what's physically meaningful is not the matrix element, but the expectation, so I have to normalize. And then there's a nasty little twist that in the Schrödinger equation that's non-relativistic, I have to normalize by mod psi plus squared, because the Schrödinger equation only knows about psi plus. But in the relativistic world, there's another bit of psi minus, and it's only in the combination of those two that's preserved. So the matrix elements, this is the same as that, but the expectation is not the same as that expectation. But luckily, using this, I can express the expectation of the extra bits in terms of H minus. So I can get an approximation for the non-relativistic Schrödinger energy expectation in terms of the matrix element I know how to calculate, but I've got to have this weird extra thing down in the denominator. So that's the piece of machinery as mass. Now, what does it tell me about numerical schemes? So here's my Fort-Frankel scheme I showed you before, and I'm going to plate the same kind of time-dependent change of variables up here, inspired by trying to get rid of this term with the exponential up there. And then I guess an equation with real coefficients. That's this one here in the middle. And that's something familiar. That's the same as the Abnovitz-Kruskal-Laddick discretization of the Klein-Gordon equation. So that's this. So we've taken the numerical scheme for the Schrödinger equation, minding its own business, being non-relativistic, and we've done a change of variables, and we've ended up with a previously known discretization for a relativistic equation. That's the Klein-Gordon equation in C equals 1 units here, and there's an effective mass I called M twiddles, which has a little near identity correction, just you can mop up some of the finite time effects by doing this slightly different mass, but as delta t goes to 0, so you converge, M twiddle and M are just the same thing. So I've gone from numerical scheme for Schrödinger by a discrete interaction picture to numerical scheme for Klein-Gordon, and now I can take this apart by saying, just as I can introduce a D in terms of derivatives of U to turn Klein-Gordon back into Dirac, I can break this 3-time level scheme for U into a 2-time level scheme for a U and a D, and then we get back to the discrete time quantum walk. That's this thing, also known as the quantum cellular automata, and also the quantum lattice Boltzmann equation that Sarah and colleagues have studied. I should just mention that there are similar results by Anne Connor and Dellar, who's one of our hosts when you were in Paris a few years back, doing the same thing for the real Fort-Frankel scheme to real D12Q lattice Boltzmann. Sort of the comment here is that both that it's complex and quantum mechanical, and also it's relating schemes which have sort of more physics behind them than, we've gone to a scheme that people actually, a PD that people actually care about independently rather than just being a numerical thing. And then this discrete time quantum walk, I can break up into 2 pieces and say it's a composition of 2 unitary operators, our lattice Boltzmann friend stream, which just moves U and D to adjacent grid points every time step, and I've assumed periodic boundary conditions, and a thing called collide loosely, which here is spinning around the U and the D wave function values at different time steps. So I wanted to just get rid of this thing at the bottom. Come on back. There we go. So the stream exactly solves the pure advection bit, and the collide solves the pure algebraic bit down at the bottom right with no streaming. So we stitch the 2 together, we get a scheme that's equivalent to the Abnovitz-Kruskal-Laddick scheme for the Klein-Gordon equation. It's equivalent to the Du-Fort-Frankel scheme for the Schrödinger equation. It all ties together under these unitary transformations. So now look at some consequences of that. So there was a mysterious invariant in Wu's paper, who said, look at the bottom, this thing is conserved. Now, you think, okay, fine, where does that come from? So we've got this 2 time level formulation that takes u and d at time n to u and d at time n+1. That's unitary evolution. That's clearly defined when we're doing 2 time levels. So it conserves this relativistic total probability, which has got a u and a d in it. And from my previous formulae, so let's go back. Back. So it's got a mind of its own. I can solve this one to solve for d in terms of the u's at the different time levels. So I can get rid of this, plug in d in terms of u's, and then I get this mess, which is now just in terms of u, and then my u, I have to undo some transformations to get back to the psi. When I get back to the psi, that this mysterious thing that Wu presented more or less out of nowhere is the relativistic probability conservation. And it sort of knows it's a relativistic scheme, so it conserves this, but it doesn't conserve these bits by themselves, which is what you'd expect for just the Schrödinger equation. You have this other bit, which comes from saying this is relativistic probability conservation, not non-relativistic probability conservation. So now I just quickly whiz through some numerical experiments. We take a Gaussian wave packet. That's an exact solution of the non-relativistic Schrödinger equation. Only depends on time through this ratio T over M, and it spreads out as time passes to make this expanding wiggly thing. And then if I fix the particle mass, I refine my spatial grids. What I find is I converge the solutions of the Klein-Gordon equation. I don't converge the raw solution of the Schrödinger equations, but the more massive my particle going down this, making my particle heavier and heavier, I do better and better. But I always notice that the relativistic effects always come in if I make my grid fine enough. I can converge the Schrödinger equation if I make my particle heavier and heavier. So then its momentum, whatever it is always small compared with c times m, because I just keep making m bigger. Then I get second order convergence under this, what you might call a diffusive scaling, toward for the phi plus, that's down here, and only first order, sadly, for the psi minus. But it does converge to Schrödinger solutions if you make the particle heavier and heavier, so it's more and more non-relativistic, as well as being more and more refined in space and time. So now, where are we? I can take that 2 time level scheme, I can make it second order accurate by doing instead of collide and then stream, I can do half collide, stream, half collides. That's a second order strand splitting. You can also wrap that up into a unitary change of initial conditions. Then I can define a P and an M, which look like my psi plus minus. So I'm just undoing my unitary transformation. I then get this new scheme here for P and N. That's unitary, it's second order accurate, and it's a discretization of those things I showed before, trying to get to the non-relativistic limit. It also coincides if I've got massless particles. So these things are all just one. This is the Lax-Friedrich scheme for P and M just affecting each other. You think, well, surely Lax-Friedrich is dissipative, but not when you're exactly on Courant number 1, which these lattice schemes always are. There are then 2 discrete invariants of this scheme, total probability now in terms of P and M squared. And this thing, I'll explain on the next slide, it's the expectation of the evolution operator. So it's combining P conjugate at time level N with P at time level N+1, ditto for the M's. Why should I care about that? Well, any unitary evolution conserves the expectation of its own evolution operator. So if we look at the expectation of U here, time N+1, U psi N+1 is U times psi N. I pop that in. I take the U over to the other side as the U dagger Hermitian conjugate, use unitary. So this red thing is just the identity, and I get the expectation at the earlier time. I also know that U approximates the exact evolution, that thing I had on one of my first slides. So if I expand for small delta t, I can replace U by this exponential up to some error, depending on how accurate my discretization is. Now expand for small delta t, I get this thing, that's the normalization, that's real. I get this thing, expectation of the Hamiltonian, thing I want because that's my energy. This thing which I know is real because H and H squared are self-adjoint, and a little thing. So I know H, the expectation of it is to do with the imaginary part of this invariant, the expectation of the evolution operator. And from this, I can play my non-relativistic games, pop this thing down in the denominator, and I get a discrete invariant that approximates the expectation of the continuous Schrödinger Hamiltonian. And then I can tell you that that actually works. So as I refine my grids, I converge towards the expectation of the true Schrödinger Hamiltonian. And if I don't mess about with that normalization in the denominator, that's this strange little shift, because it's the scheme conserves the relativistic property. The expectation is defined with the non-relativistic probability. If I don't do that, then I saturate and don't converge anymore. But if I do it, I can keep converging down as I keep refining my grid. So I'm sorry I've run slightly over, but if I can just sum up. I talked to you about Wu's Fort-Frankel scheme for the Schrödinger equation. It's explicit, it's unconditionally stable, it's only conditionally convergent. So it's not guaranteed to converge to a solution of the Schrödinger equation as you refine the grid. Under unitary transformations, a kind of discrete interaction period, picture, I can map it to this AKL discretization of the Klein-Gordon equation. I can map it to the discrete time quantum walk, the quantum lattice Boltzmann equation, all discretizations of the 1D Dirac equation. So in this sense, it's generating unitary evolution for a first order system for U and D. Wasn't clear what that meant for a 3-time level scheme for psi. It only converges to Schrödinger solutions if you're non-relativistic as well as refined. That explains the conditional convergence. Wu's mysterious invariant says, really, we only conserve relativistic probability, not non-relativistic probability you'd expect for the Schrödinger equation. And there's a second discrete invariant which does express conservation of the discrete non-relativistic energy. And then more details and references are all in this paper. So thank you very much, and I'm sorry I overran slightly.
Thank you very much, Paul, for your this very kind presentation and very interesting. We have room for some questions. This was the last presentation for today. Are there any questions from the audience?
Can I ask you a question?
Please, Alex, of course.
Yes. Hi, Paul. It's a very interesting presentation here. So this, if I understood this right, there is this fundamental connection between the Schrödinger equation and the relativistic versions in some limit, and almost by accident, some of these discretizations then recover more with these relativistic solutions. Do you have any idea of how you would? So this was, if I got that right, mostly for one particle. Do you expect this to be practical for more particles than one?
It's a shame. I think Bruce is chairing the upper session because he and somebody, Taylor, I forget his first name, worked on this some years ago. But the problem is, to do it properly, you then start having, if you want two particles in one dimension, you have it's a two-dimensional space. So the dimensionality just goes crazy unless you do some kind of approximation. Mm-hmm. But so to answer the question, which I thought you might ask, is why is this? So it seems like if you want any numerical scheme that satisfies certain plausible properties for quantum mechanics, that it's explicit and it generates local unitary evolution, and you're trying to do one particle, you seem to be led back to this same place. And it's, in some ways, it's relativistic because it has to be. And it's a bit like, blowing my own horn again, that when I set out to try and do MHD nearly 20 years ago, I realized quite a long time later that I'd also done Maxwell's equations by accident, because you can't do the MHD, the sort of the pre-Maxwell non-relativistic thing by itself in this kind of first order hyperbolic system framework, which is the PDE system that all these kinds of lattice-based numerical schemes most closely relate to. I had to have done Maxwell's equations to make it work. So here, if you want explicit local unitary evolution in quantum mechanics, you basically have to be relativistic at the same time. Yeah, it would be nice to say, so people like David Mayer sort of looked at this saying, what kinds of quantum cellular automata can there possibly be with plausible properties? So maybe there's some result out there saying what kinds of numerical schemes with plausible properties are there? And they all seem to boil back down to the same one under unitary transformations. So I'm afraid that's more asking the question that you didn't really ask, but sort of alluded to. And Bruce would be the person to ask about, I think, the question that you really asked me.
Okay, thanks. Are there any other questions? Okay, if not, I would like to thank Paul one more time for this nice presentation. And I would really, really love to thank you all for being here today, for opening this conference with these very interesting presentations and topics. They were really wonderful. I really enjoyed being the chairman for today. And I leave you telling you that in the chat I paste the YouTube channel on which we are uploading the presentations, so you can see them back. And I greet you all, wishing you a wonderful evening, afternoon, or night, according to your position in the world. And see you tomorrow morning for the next presentations. So thank you all really one more time, and see you tomorrow. Bye-bye, good night. Thank you all very much.